My name is Karen Daly and I teach mathematics at DKIT, a third level college in Ireland. This video was produced to further assist my first year computing students with their mathematical studies. At the end of this tutorial, you should have an understanding of how a computer represents floating point numbers. Enjoy! So let's look at this example. It says write the 32-bit computer representation of 936.35, which is stored as a floating point number using the IEEE format. The 32 bits that the computer uses to store this number is broken into three distinct parts. The first part is here. It's of length 1 bit and it's used to store the sign of the number. If the number is positive, what we do is we put in a 0 into this position. If the number is negative, what we do is we put a 1 in this position. Now our number here is 936.35. It's a positive number, so what we do is we put a 0 in the first bit. The next 8 bits hold what's called the exponent value, and that tells us the size of a number. The last 23 bits holds the significant, and that tells us the finer detail of the number. So we want to find the 8-bit exponent and the 23-bit significant, and to do this we're going to use a formula. This formula will be given to you in the exam. So this is the formula. It says that the closest binary number to y that can be stored by a computer in 32 bits is given by this. Now what I'm going to do is I'm going to put a box around, a red box around all of this, right? And what I'll tell you is you don't have to remember this. This will be provided to you in the examination. But what you have to do is use this information to find the value of the exponent and the significant. So how do you do that? So let's go back to the top of the page again. It says that the closest binary number to y, right? That's the first thing we come across. Well, what is y? Well, y is actually the number that's given in the question. It's 936.35. That's the number that we're asked to find the computer representation of. Now, if you look at the formula here, z I can work out. Z is actually equal to the absolute value of y. Now, all the absolute function does is that if the number is positive, it just reports back the number itself again, whereas if the number is negative, it gives you the positive part of the number, so it gets rid of the minus sign for you. Why we need to get rid of the minus sign is when we go to work out p. P involves a log, and obviously you can't get a log of a negative number. So let me work out p. P is equal to the floor of the log of z to the base 2. We have the value for z, so this is equal to the floor of the log of z, which is 936.35 to the base 2. Now, you may have a calculator that can work that out directly. It should be looking something like this as a button log of, let's say, x to the base a, where you put in the value for x and a and work it out directly. If you don't have a calculator that does that, you can do a simple conversion, and it's just the floor of the log of that 936.35, I'm running out of space there, all divided by the log of 2. And you can work that out as a calculation and you should get the same answer. So what the answer turns out to be is that it is the floor of the value 9.87, and there's a good few more digits after that, but I won't write them in. Now we need to understand the floor function. The floor of x is the integer that is directly below x. Alright, so in our case here, the floor of 9.87, 8.87 is ignored, and you just bring it to the integer that is below that, so it's equal to 9. Now let's work out the value for j. Right? J has p in the formula, so you have to work out p before j. So let me just move the page down a little bit and do that. Now the formula for j is that j is equal to the round, right, to the nearest integer of 936.35 multiplied by 2 to the power of 23 minus p. So it's 23 minus p, which is minus 9. 23 minus 9, of course, is 14. So again, it's the round of this 936.35 multiplied by 2 to the power of 14. Now, you take out your calculator and you work that out on your calculator, and what you'll discover is the answer turns out to be that it's the round of this number here, very big number, 15341 158.4. Now I'm rounding it to the nearest integer, and how to round to the nearest integer, what I do is I go to the number that's to the right of the decimal point. If it's a 5 or greater, I add 1. If it's less than 5, I leave it alone. So you can see here it's less than 5. So the round of this number is 15341 158. Now if I go back up to my formula, I'm now in a position to work this part of the formula out. And this is going to give me the closest binary number to y that can be stored in the computer using the 32 bits, right? Now, what you notice here is that I need j in binary, right? So what I'm going to have to do is I'm going to come back down here and I'm going to work out j in binary. Now j is a very big number, so I can't do the conversion directly on my calculator. So what I'm going to have to do is I'm going to have to convert this number to hex first. So I'm going to take 15341 158 and convert it to hexadecimal first on my calculator and then convert it to binary. So if I do that, I discover that in hex this number is EA1 666 in base 16. Now to convert that to binary, what I do is I replace each digit by its 4-digit binary equivalent. And what I get is E is 1110, A, bring it over here, is 1010, 1 is 0001, 6 is 0110, and there's 3 of them, 0110, 0110. So that's the number j in binary. Now let me draw your attention to the fact that there are actually 24 bits in this number if you were to count them. You've got 1, 2, 3, 4, 5, 6 sets of 4, so there's 24 bits in this number. Now let me move down a bit to give me a little bit of space. So the part of the formula I'm focusing on at the moment is this. I've got now j in binary. I have the answer to that. Here it is here, right? I know what my p-value is also. P turned out to be 9, okay? And I also know that s is equal to 0 because my y value is greater than 0. So this value here, all of this, any number to the power of 0 is 1. Okay, so we can gladly ignore this for the moment. If we take this j value in binary, this number up here, right? If we divide it by 2 to the power of 23, essentially there's a fractional point understood here, and if you divide by 2 23 times, basically it moves the fractional point for you back this direction 23 places. So the fractional point is going to end up here, right? So let me write that down for you, right? It's going to turn out to be 1.110 1010 0001 0110 0110 0110, right? So So the fractional point is now here because you divided by 2 to the power of 23, and all I'm left with then is multiplied by 2 to the power of p, and p has the value 9. Now let me just move this up again and give myself a bit of space. There will always be a leading one here. This is a leading one. And what the computer does is it presumes it's there, so it doesn't store it. Alright, so it knows it's there, but it does not store it. What you're left with here are 23 bits. And this 23 bits becomes your significant. So this is what the computer stores as for the finer detail of this number. So just let me put a box around that. So that whole part there is going to become our significant. Now to work out the exponent that we need. The exponent is going to be equal to this value up here. In this case it's the 9. So it's 9, right? And it's we're always going to add 127 to it. The reason why we add 127 is purely that this is how the computer is designed to store and do arithmetic with floating point numbers. So if we do this addition, we'll get 136. And obviously it will store 136 in binary form. So if we convert 136 to binary, what we'll get, you can do this directly on your calculator, you'll get 10001000. Obviously if you had, there's 8 bits there, so it is 8 bits, but if there were less than 8 bits, you'd fill out the places with zeros before you'd put in the number to make up the 8 bits. So now we have the solution. Let's fill it out. Remember, the first bit was the sign bit. Our number was positive, so we had a 0 in there. The next part of the number was the exponent. I should write down the sign as well. I'll do that. Sign. All right. The next part was the exponent, and I'll just put a box around it here. We've discovered that the exponent is that number there, 10001000. Right? There's 8 bits in that. And the last part is the significant. The significant. Right? And we have found that's up here, right? And if we just write that in, we'll get 110, 1010, 0001, 0110, 0110, and lastly 0110. So this is the solution. This is how exactly your computer stores the floating point number 936.35 in 32 bits. The computer is a finite machine, and it's limited by, in particular, the storage space that it has to allocate for each task. In this case, it allocated 32 bits to storing this number. So what it does, if we read here from the top, is the computer stores the closest binary number to y using the 32 bits it has allocated to the task. And unfortunately, this is not necessarily the exact number you requested to store. In fact, for our case, when y is equal to 936.35, which was our example, the number that is actually stored by the computer is given by this formula here. So we can work that out for our particular example, because we have the value for s, remember, was 0, so that just turned out to be this part here. S was equal to 0, so that part just turned out to be a 1, right? We have a value for j, so the number that's actually stored by our computer is j, which turns out to be 15341,158 divided by 2 to the power of 23 minus, and p turned out to be 9. Right? So if I work that out, I'll get that it's 15341,158 divided by 2 to the power of 14. So if you work that out on your calculator, what you get 936.349975. So you asked your computer to store the number 936.5, but what your computer actually stored for you was this number here. This fact can obviously have implications when you go to do lengthy calculations, so you need to be aware of this. What we just looked at was a 32-bit computer representation of the floating point number, which is called single precision, and it gives you an accuracy of about 7 decimal digits. You can also double this, called double precision, which will give you 64 bits to store the number in, and obviously that will increase the accuracy of the digits stored up to about 16 decimal digits. And you can go beyond this again to a long double precision, which will give you 80 bits and an increased accuracy also. For this tutorial, we're going to stick with the single precision 32-bit computer representation. Now let's look at this example. We're asked to write the 32-bit computer representation of the negative number 936.35 stored as a floating point number using the IEEE format. This is exactly the same as the last example, except I have a minus in front of this number, so it's the negative 936.35 I'm going to look at storing. So exactly the same as before, our 32 bits are split into 3 different parts. The first part is the sign bit. Now this is different from the last example because this here is a negative number. And if it's negative, the sign bit is equal to 1. So that's what our case is here. So the very first bit is a 1. Right? Now, if we start the process off and we write down our y value, well, y value is equal to minus 936.35 because that's the number that we want to represent. If we go ahead then and work out z, z is equal to the absolute value of y. And what the absolute function does is that if it's negative, it changes it to a positive number. So the absolute value of minus 936.35 is the positive 936.35. Now you go ahead and you work out p, but p turns out to be exactly the same as before because we're using the same z value. Likewise, we work out p and then j, and j is exactly as we had before also because we have the same z value. There's a slight difference in the closest binary number to y will have to be a negative 1 point. It turned out to be 1.11101010 all the way up down to the last one, 0110 by 2 to the power of 9. So the only difference is that I have to put in the negative value there because it's a minus number. This will make no difference though to the significant nor to the exponent. So the computer representation of the negative number is exactly the same. So let me put in the values that we had got. The exponent was 1000, 1000, and the significant, if you recall, was 1110. Sorry, just noticed I put in an extra one there by accident. So if you take that out there and take that out there. Okay, so it's 110, and then it's 1010, 0001, 0110, 0110, and 0110. So that's the answer. So the computer representation for the negative 936.35 is identical to the computer representation of the positive 936.35, the only difference being this first bit, the sign bit. When it's negative it's 1, when it's positive it's 0. Let me do another example for you. It says write the 32-bit computer representation of the number 0.0123 stored as a floating point number using the IEEE format. Underneath this video you have access to a Word file with the formula appropriate to doing this question. What I suggest to you is to print this formula out and have it beside you as I work through the problem. So firstly, I write down what y is, and y is what I'm asked to represent. Y is equal to 0.0123. Then I write down the value of z. Z is the absolute value of y, so there's no change because it's already positive, so it's 0.0123. Then I go about working out p, and p is equal to the floor, right, of the log of z, and z is 0.0123 to the base 2. So that turns out to be the floor of minus 6.34. Now flooring a number brings you to the integer that is smaller than the integer represented in the bracket there. So the integer smaller than minus 6.34 is equal to minus 7. So be careful of that, your negative numbers. Now if we go ahead and work out the value for j is equal to the round of z, and z is 0.0123 multiplied by 2 to the power of 23 minus p. And remember p is minus 7, so be careful there. A minus and minus is going to give you a plus. So it's equal to the round of 0.0123 by 2 to the power of 23 plus 7 is 30. Okay. Now if you take out your calculator and work that out, you'll get 132,07024.44. And sorry, it's the round of that, so let me just take out that and put in round. So it's round of this here, and there's a decimal point there. So if you round this number, you go to this here. If it's 5 or greater, add 1, which it's not, so we just leave it alone. So it's 13207.024. Next stage is to convert j to binary. So we're going to write j in binary, and to do that we're going to have to take this number and bring it to hex first. You can do that directly on your calculator, and what you'll discover is that it's C985F0 in base 16, right? So in binary, C is 1100, 9 is 1001, 8 is 1000, 5 is 0101, F is 1111, and 0 is 0000, and now you're in base 2. Now we find the closest binary number to j, which is given by the formula, this here. So I'll just write it out just to make sure that you have that, right? So all that does is s, as I said before to you, s is positive, the number is positive, so s is equal to 0. Any number to the power of 0 is equal to 1. So that just turns out to be 1. We have j in binary, and now we just put in the other things. Dividing by 2 to the power of 23, there's 24 digits in j, 1s and 0s. So it just has the effect of moving the fractional point from here up to here. So when we do all of that, what we get is that the closest binary number to j is equal to 1.100, 1001, 1000, 0101, 1111, and 000. And it's multiplied by 2 to the power of, sorry, I'm going over that, p, and the p value is, what did the p value turn out to be? Minus 7. Okay. Here's your leading one, right, which the computer knows is there but doesn't choose to store. So what you're left with is this here then, which provides you with your significant. So that's the significant that's stored for that number. Now let me just move down a little bit to give myself a little bit more space just to finish this problem. Okay, the next thing is the exponent, and the exponent is equal to this value up here, which is minus 7, and you always add 127 to it. And that value then turns out to be 120. Obviously you need to convert that to binary, and 120 in binary turns out to be 1111000 base 2. There are only 7 bits there, right? And you need to store it, the exponent, in 8 bits. So if you fill out to 8 bits, what you'll get is that the exponent is 0, 1, 1, 1, and then 1, 0, 0, 0. So now I have everything I need to write out my solution, how this number is stored, and how the computer sees it. So the first bit is the sign bit. It's a positive number, so I put a 0 in here. The next 8 bits are the exponent, and I have them there. I'll put a box around them. So I'm going to fill that out. 0, 1, 1, 1, and then 1, 0, 0, 0. The next 23 bits is the significant, and I had already found that. That's up here. So it's 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, and lastly 0, 0, 0, 0. So that's the answer to my problem. That's the 32-bit computer representation of the number 0.0123. Just to emphasize the point again, so what the computer has stored with these 32 bits is the closest binary representation of the number you want it stored. We can actually look at the actual number that is stored by the computer for our number. And so if we fill in what we know, well, s is equal to 0, any number to the power of 0 is 1. If we put in the j value, let me think what the j value was. It was 1320724. That was the j value, divided by 2 to the power of 23 minus p. P was minus 7, so 23 minus 7 is going to give me 2 to the power of 30. And if you work that out on your calculator, you'll get that at 0.0122, and then all the rest are 9s. There are 5 9s on my calculator after that. 1, 2, 3, 4, 5. So this is an actual fact. What the exact number to whatever precision, how many decimal places there, and that the actual computer is storing to represent the number 0.0123. Now what I'd like you to do is to try this exercise yourself and write out the 32-bit computer representation for, firstly, the positive number 0.04, and secondly the negative number minus 0.085, as they are stored as a floating point number using the IEEE format. So just repeat what I have done for these two numbers. So turn off the video, give yourself a little time to try that, have the formula in front of you as you're working through it, and see how you get on. Then come back to me and I will put up the solutions for you. How did you get on? Hopefully you got on okay. Here are the solutions for part A and B. These are the first, I've listed the values for Y, Z, P and J for both parts. And then lastly here down at the bottom, I've just written out the entire solution, the 32 bits that represent both of the numbers.